Hello, guys and gals, and welcome to what is hopefully our last video for this unit, part one. Anyway, we're going to be going over the final practice problems. So if we look at practice problem 16, they've given us a reaction, the decomposition of N2O5, and they told us that they recorded the partial pressure as the reaction was occurring. And if we look at this graph or table that they've given us pressure, natural log of pressure, and reciprocal of pressure data versus time, of course, right? So we have to ask ourselves, can we use pressure data the same way that we can use concentration data? Is that allowed? The answer is yes, because pressure and concentration are directly correlated. And what that means is when pressure decreases, concentration is going to decrease. And when concentration decreases, pressure is going to decrease is the better way to say that, right? If we think about it, it makes sense. If our concentration decreases, our number of moles, our number of particles decreases. The less particles you have, the less times they're going to hit the sides of their little box or container. And the less you hit the box, the lower your pressure is. So the lower the concentration, the lower the pressure, and vice versa. So we can use pressure data with gaseous reactants to help us determine orders and rate laws and all those kinds of things that we would use concentration for. So let's take a look at this one. Now, they've given us the information, but they haven't given us the graphs. Well, I don't know about you, but I'm kind of awful at sketching graphs. So what I'm going to do to solve for this is I'm going to put these points into y equals mx plus b, and I'm going to see which slope actually leads me to the data points that they've given me, okay? Now, I think in class a couple of times I've said incorrectly that your slope should be close to 1. That's actually your r value that should be close to 1. Your slope, however, should work with the y equals mx plus b equation. So let me show you what I mean. Y equals mx plus b, where y is the y point we're looking at, m is your slope, x is your x point there, and b is your y-intercept. So I'm going to make this nice and easy for myself. For just pressure, I'm going to say 75 is equal to m, because that's what I'm trying to solve for, times 100, because that's the time where my y point is 75, plus my y-intercept, which is 150. Now remember that with pressure, or with first and zero order, your slope is going to be negative. So when we start solving this here, we're going to get a negative 75 is equal to m times 100. And that's okay. Even when we divide by 100, we're going to get negative 0.75 is our slope. And that's what we expect to see. So let's stick this slope back into that equation with a different point and see if it actually solves for it correctly. So if we'll solve for y, our y value is negative 0.75. We'll multiply that by the point at 200. So when I solve for this, my y value should be 38 plus 150. Okay, so times 200 plus 150. Okay, well, that's not what I get. I get that my y value should be 0. So what that's telling me, since this answer does not line up with that data point that's on the graph that's on the table that was given to me, that's telling me that this graph does not have a linear slope. Okay? Because if it was linear, the y equals mx plus b equation should be able to predict my y point at that time. Okay? So let's try the next set of data. Y equals mx plus b, where y is going to be 4.3. M is what we're solving for, x is 100, and our y-axis was 5, because that's the point at y when our time is equal to 0. Again, we should find that we get a negative slope because this is first order, and that is exactly what we're going to see. Divide by 100. We'll end up with negative 7.0 times 10 to the negative third, and that is our slope. Okay, so let's stick this back into the y equals mx plus b equation and see if it accurately predicts the data points that they've given us. So we're going to solve for y when m is negative 7 times 10 to the negative third times 200, and our y-intercept does not change at 5. So let's try it. Times 200 and then plus 5, and we get that y is equal to 3.6. Well, at 200 seconds, did our table tell us that y is equal to 3.6? And the answer is yes. So it's the first order that's giving us the correct information. It's giving us the correct slope. The first order graph would be linear. You could go through and try it with your second order data too, and you will find that it does not work out. So the correct answer here is B. The decomposition is first order. So for question 17, the rate constant for the decay of a radioactive isotope is given to you. So that's the K value is given to you. The slope of which of these graphs is correct? Well, later on we'll learn that all radioactive decay that you'll talk about in AP is first order. But for now, the reason I put this in here is because I wanted you to pay attention to the units. This unit is time to the -1, or 1 over time. What that means is you have a first order problem. If you have a first order problem, then your y-axis should be natural log. Okay, so in the future, you'll know that all radioactive decay that you'll work with is going to be first order, in AP anyway. But for this problem, I wanted you to pay attention to the units. We have a hard time paying attention to units, so make sure that you know them, okay? This last problem here is a lot bigger. Couldn't stick it in one box, but it's very good because it's going to show us the relationship between absorbance and rate. So what they've done is they've mixed blue food coloring with bleach. It's going to make a colorless product. So if we can look at the absorbance over time of the blue, we can see how fast the reaction is occurring between these two things. And here they've given us absorbance, natural log of absorbance, and 1 over absorbance times versus time for all three of these, right? So just like we could use pressure in place of concentration, we can also use absorbance in place of concentration. And this is because absorbance and concentration are also directly related, right? So based on the graphs above, what is the order of the reaction? Well, it's easy to see that because the natural log is the only linear graph, this is going to be a first order reaction, okay? As we scroll down, it says the reaction is known to be first order with respect to bleach. In the second experiment, the student prepares more, but with different concentrations. So it's the same setup as the first one, but it just has different concentrations. What they find out is that the reaction mixture reaches an absorbance of 0 way too quickly. Your reaction is happening too fast. So how can we modify the experiment to make it actually go slower? Now, here's the thing. All of these here are telling us that they should speed up the reaction. Each thing here is telling us they should speed up the reaction. Because increasing the temperature does, heat them up, speed them up. Increasing the concentration does. So how does it make sense that one of these is going to slow down the reaction? Well, we have to think about what's happening. If the blue is disappearing too quickly, that means that the blue must be the limiting reactant, which we already know that it is. The bleach is in excess, it told us in the previous problem, right? But if it's reaching too quickly, that means that the bleach is in serious excess, right? It's happening so fast that the blue hardly doesn't even have time to exist. So by increasing the concentration of our food coloring, we're going to force that reaction to go slower just because there's more blue food coloring, and so our absorbance is going to be changed slower, okay? Hopefully that made sense. Come and see me if it didn't. In another experiment, they want to study the oxidation of red food coloring instead of the blue. So how are we going to have to change our experiment? Well, it doesn't say they want to change anything else except for the color of the food dye. So could we leave everything the same? Not really. Remember that spectrometers read absorbance. So if you shoot a high frequency light at a high frequency color, it's all going to be reflected because the color that we see is the color that's being reflected. Red is a very fast frequency, like a high frequency color. It has a very fast wavelength, okay? Blue is very slow. So when we see blues and darker colors like blue, we're going to shoot a fast light at them because the blue is not going to reflect fast light. It's going to absorb fast light and only reflects the slow light that blue is. So if we're red, we need to change it to the opposite. We need to change the wavelength on the spectrometer to be the opposite of what red is reflecting. So if red is reflecting high wavelength or fast wavelengths, we need to make it absorb slow wavelengths. Okay, I hope that made sense. Come and see me if it didn't. I'm trying to go through this a little fast, but that is the end of this. Please make sure you're keeping up with your homework problems because you won't be too overwhelmed if you do, okay? Let me know if you have any questions, guys. Maybe. There we go.